Okay, so welcome to the third and final lecture on time domain astronomy. We're going to go over three topics. They're sort of a continuation of what we've been talking about the last 2 weeks. So the first topic is period estimation. In particular, we'll talk about quantifying uncertainty on period estimates. We talked a little bit about period estimation at the end of lecture last week. And then we'll talk a bit about modeling, instead of using generic models like sine functions for light curves, we can fit tailored functions that are specifically designed to capture information we know is in the light curve shapes. And this can improve parameter fitting and allow us to do science with very poorly sampled light curves. And then finally, I'll talk about an application of finding structure in the Milky Way halo using RR Lyrae periodic variable stars. Okay, so just to refresh the model that we're talking about. So remember, we're talking about variable stars, and we have a sinusoidal model, say, for the brightness variation. So the magnitude at time ti is yi, and that's a constant magnitude beta 0 plus a sine function with amplitude a and phase phi, and some measurement error, which we'll assume is normal. If we want to find the maximum likelihood estimate for the frequency omega, we just minimize the sum of squares. In astronomy, this is often called chi-squared minimization. So we can get that estimate omega hat. But then we don't just want an estimate, we want some sense of what's the uncertainty in omega. So how do we assess uncertainty? So if we're working in a frequentist framework, we usually look at the asymptotic variance. So in particular, we have that for any model under some regularity conditions, the maximum likelihood estimate for a parameter, so that's theta hat ml, is converging in probability or converging almost surely to the true parameter theta. And much more than that, the distribution is asymptotically normal after centering at the true parameter theta. And the variance, the asymptotic variance, is the Fisher information, which I'm denoting by this letter I, and it has an expression involving the second derivatives of the log likelihood and then taking an expectation. So typically, when we're doing a statistical analysis, we'll report a point estimate, so that would be theta hat ml. So that would be like the result. That would be like the number we get out of chi-squared minimization, and then we also report the asymptotic variance, which would be this, and I missed a to the -1 and probably over n. Okay, so let's just look at this in a really simple case. It's a little bit hard to compute the information, the Fisher information for the full model, because there we had several parameters. So I'm just going to look at a simpler model that just involves one parameter that sort of gets at the idea. And so here it's very easy to compute the Fisher information. So the simpler model, we get rid of the intercept. We just assume that this light curve has mean 0 magnitude, and we'll get rid of the phase, get rid of the amplitude, and so we're just left with a frequency omega. And then we can look at our data as we're getting IID pairs of times and magnitudes. So those are the TIs, YIs. So the TIs are being drawn from some distribution determining when we're getting observation times, when we're observing this star. And that can be denoted by FT. And then the response, the magnitude at time t, is just normally distributed with a mean of sine omega ti and a variance of 1. So it's simple to write down the point estimate for omega here, minimizing the sum of squares. And then if we want to estimate the asymptotic variance of this quantity, we have to compute the Fisher information. So usually the Fisher information is a matrix because it's a P by P matrix where P is the number of parameters. But since I made this model super simple, the P by P matrix is just a 1 by 1 matrix and it's a scalar. So we don't have to deal with any partial derivatives or anything. So we can directly compute the information, and after some calculus, we get that the information is the expectation cosine squared omega t t squared. So we don't know several of those quantities. So even though we can compute the information mathematically, we have to estimate this quantities if we want an estimate of our variance. So in order to estimate this, we can just plug in our point estimate for omega hat, and then approximate this expectation using the observed times. So if we do that, then our estimate of uncertainty on omega has this form.
Sorry, why is it obvious going between the first and second one? Maybe I've forgotten that.
So you have the 1 over square root 2 pi. So this is a, it's not that obvious. So you have so x is the times, like xi is a time I, yi pair. So the time is the time you're observing, and the y is the magnitude. And then f of x given omega can be written as f of y given omega and then at some time t, and then your distribution on the t's. So yeah.
So what was y?
Y is the magnitude. So the idea is, you can think about this as a two-step procedure. So first you draw some time at which you're going to observe this star, and that's being drawn from some distribution f of t, or with a density f of t. And then at that particular time, you draw a brightness according to this density, and this is specified by that really simple sine model. So just sine, it's normal mean sine omega t variance 1. So then if I look at, so you'll notice that this doesn't, it's assumed that this doesn't depend on omega, the times at which you are going to be observing the star, which is realistic, right? You choose some times, and that is, you're not like choosing them as a function of omega, the frequency. So then when you take a log here, you're going to get these two components separate. When you take the derivative, this is just 0 because it doesn't depend on omega. And then this is a normal here, but so this guy is log of 1 over, I even just assume that the variance is 1 here. Which gives me that second line after moving the negative inside. So if I take the log here, this will separate, take the derivative of log 1 over 2 pi, that's 0. This is just negative y minus sine omega t squared over 2, and then the negatives cancel.
I think I was just getting confused because f isn't actually the function, it's not the sine omega t, it's actually the
You can think of f is the, so x is a vector of times and y, and then f of x given omega is just like a bivariate density, which is describing so here's time. And then you're observing, suppose you say, I'm going to observe this star in between these two times, and I'm going to just equally likely choose times to observe the star. And then suppose the true signal, it's got to be a sinusoid here. Actually has to have mean 0. So where's this? And I even specified the phase. So. Okay. And then you're going to have scatter around this. So you're observing points from this line plus error, and then this is f of x given omega is the bivariate density here in t and y space.
You also base summation. Use y and t are paired.
Yeah, so I'm computing this for a single observation, and then if you could somehow know this, then the variance that you would report is this over n. But by IID-ness, it's the same for x1 and x2 and x3.
So just to put it in my own language, I should think of f as a rho density.
Think of f as a density?
Density in parameter space.
Yeah, f is a density. It's you can think of it as the model, which is linking the parameter omega to your data y and t. So has anyone used Jupyter notebooks here before? Okay.
You have to.
So let's see if this works. Oh no, okay, it's not going to work.
Oh, wow.
So it's pretty cool. You can run Python remotely, except when the servers are full. Okay, so this is less good, but I can give you a sense of what IPython and Jupyter Notebooks can do. So you can mix together code like in R or Python and LaTeX. So it's a lot like if you use Sweave or Knitr with RStudio or just R. One nice thing is that you can run it like in a web browser, or even run it remotely if there are vacancies at that website. But what I did here is, not that I'm going to go through this in detail now, but just spelled out how to compute the asymptotic variance for this really simple model, and then did a little simulation in Python, first generating some data. So this is what data, one realization of the data might look like from this model. So I think you're observing this star 1,000 times. You can see there's a period there of variation, which you can see pretty clearly. So then I looked at 100 so the true frequency, I think, is 6. Yeah, omega is 6. So you can look at what happens if you repeatedly generate the data and make estimates of the frequency. So that's how frequentists think about uncertainty. So I did that with a few lines of Python code. Here's an example of the residual sum of squares from one generation of the data, and you can see that the residual. Oops. The residual sum of squares is, okay, I guess I actually did do that. The residual sum of squares is minimized near 6, which is the true frequency. Here is a histogram of your frequency estimates. So the result for maximum likelihood estimator says that your uncertainty around the true frequency should be normally distributed. This histogram suggests that that is happening in this particular case. In particular, you can also estimate the asymptotic variance. Here's a histogram of the standard deviations on omega, estimated according to the procedure I just outlined. You can see that the asymptotic standard deviation seems to be a little bit under 0.1. And then if you go back to the histogram of point estimates, you can see that that seems to be accurately describing the uncertainty in the point estimates. Okay. All right, some other time we'll do Jupyter. Okay, so that model I just showed is totally unrealistic because it doesn't have an intercept term or an amplitude or a phase. You can do something quite similar with a more realistic model, like fitting a sine function. The sort of challenge there is you have to deal with a lot of details, including when you're computing this Fisher information. It's now a matrix, and it's going to be, in this case, it'd be a 5 by 5 matrix because you have a mean magnitude and amplitude, a phase, a frequency, and a uncertainty sigma. But if you go through a bunch of the math, you can compute this information matrix and then invert it, and then you have your asymptotic variance as for omega as one of the components of this matrix. This leaves out some important details. In particular, sometimes there's heteroscedasticity, and astronomers tend to think they know what the variance is. So instead of having unknown sigma term here, you could have sigma i's, which are known, and you could get rid of, essentially get rid of this term. So that would be one modification to the model. A second issue is that we talked about this sine model as sort of an approximation to what the true shapes of light curves are. So if the model is incorrect, then is your estimate of the variance, does it make any sense? So I don't think people have looked into this too much in for standard linear models. If you have say y is a nonlinear function of x, sometimes people still do linear regression. You get some line there, you measure your uncertainty on your line, and you can use something called a sandwich estimator, which gives you the correct uncertainty even when your model is wrong. So something like that might be applicable here. And then the third issue is infill versus outfill asymptotics. Do people know about infill versus outfill asymptotics? No? One? Okay. So this is a kind of a big thing in spatial statistics, but it's relates to how you're sampling these times. So I said that you just have some, your data is IID, and you have some t that some density t that you're sampling from. That might not be a good approximation in astronomy cases, because usually your next observation is going to come sometime in the future. So you're going to observe maybe sometime during the next night. So if you have n observations, those might be one observation per night for n nights. And then that's sometimes called outfill asymptotics, because the sort of domain over which you're observing the process is expanding. It's like outfilling. And so infill asymptotics is when you're sort of filling in a fixed domain. So those have the asymptotic rates can be quite different for infill and outfill asymptotics. Practically, I'm not sure if it makes a huge difference. So people sometimes do models for if they're doing asymptotics for period estimation, you can do asymptotics where you observe like one observation per night. So your next observation is approximately 24 hours after your last observation. And then you get there's some modifications that are needed here. But roughly you can get a measure of uncertainty on your period. Okay, so I think in doing astrostatistics, it's important to keep in mind the larger goal. So you don't just have one star where you're trying to estimate a period for it and quantify uncertainty. You might be doing something like trying to estimate a period luminosity relation. So I talked about that last week, right? Do people remember what the PL relation is roughly? Okay, I'll review it quickly. So every point here is one variable star. So you have a light curve for each one of these points. And then you can estimate a period for that light curve, and you can estimate. Okay. You can estimate the mean brightness of that star. So it's I guess I have it on the next slide, right? Oh. So for each point, say, there's an associated light curve. And associated with that light curve, there's a period, P, and there's going to be you could say just a mean, M, or L, I'll call it luminosity. And then you can make a scatter plot. So you get a lot of these light curves, like a few hundred. Then you make a scatter plot, you see this linear relationship, and then what's one thing that's really important is that the y-intercept for this linear relationship can tell you how far away all of these objects are. So all of these objects, they're in the same, in roughly the same distance, maybe in the same galaxy. You make this plot for them, you find the y-intercept, and then the distance to this galaxy is a function of the y-intercept. So if you're thinking about, okay, I have a bunch of variable stars, I'm estimating periods for them. Of course, there's uncertainty on the periods. What you're possibly most interested in is, okay, there's uncertainty on this period. That is essentially causing uncertainty here on the x-axis for each of these points. And then that uncertainty is going to cause uncertainty on my y-intercept for the linear relationship I estimate here, and you want to propagate that all through. So one question is, how is uncertainty here affecting the uncertainty on that y-intercept? And in particular, if people are familiar with errors and variables models, at least a little bit, you'll know that when you have if you have a linear relationship between x and y, and but the x's are observed with error, then what that does is if you just fit a line and you ignore that error, it causes attenuation bias. So the slope is biased towards 0. Are people familiar with that, I think. So one thing you might be concerned about is, okay, I have the relationship between the true period and the luminosity is linear, but I have estimated periods that's causing the slope to be biased towards 0, which is going to cause my estimate to the distance to this galaxy to be biased somewhere. So you want to think about that when you're like, what's the whole process going on here? We're not just looking at one variable star, we're looking at there's several steps in inference process. So just to kind of explore this issue, I took one of these variable stars at random. So this is just the first row of the table. So that's this orange dot. It's a little hard to see. It's sort of an outlier, but that was just totally by chance. Not a huge outlier like this guy, but a little bit of an outlier. And then, so here's the light curve for that variable star. So you're observing how bright it is over time. And then roughly the luminosity, the y-axis component of the last plot would be the mean here. And then you have to estimate a period. So you can use one of these period estimation algorithms we've been talking about, like just fitting a sine function. And then you can fold the light curve, and then you can look at the folded light curve, and you see this. So it looks at least, roughly correct. The question is, though, how much uncertainty is there? Could it be that actually, I mean, we got the period at least roughly correct, but could it be way over here or back here? So one thing that you can do with these light curves is you can look at them folded on a slightly different period and then see, does the fold, does it look like you have a clean signal? So here's the light curve folded on the true period, or the estimated period plus 0.1 days. So just a tiny bit difference. And you can see that looks totally like junk. So your uncertainty is less than 0.1 days. And here's with 0.01 days, and it still looks like junk. And when you get down to 0.001 days, so 1/1000th of a day, then you can see that this is getting in the range of plausible, but the folded light curve doesn't look as good as when it was folded on the estimated period. Here is with 1/10,000th of a day off. So it looks like that your error on estimating this period is below 0.001 days. And what that looks like how that error then affects your PL relationship, you could kind of approximate here. So here's the point again. And then I've zoomed in on a very narrow range of the x-axis, so between 0.35 and 0.32 days. So that's here. And then these two vertical black lines are the sort of range of error that you can actually just get by looking at the light curve. So those are each of those black vertical lines is 0.001 days away from the estimated period. And you can see that there's very little uncertainty, right, on the period estimate. So probably any uncertainty on that period estimate with light curves that are this well sampled can effectively be ignored when you're making the PL relation. So you can also determine that with an asymptotic analysis. So if you computed the Fisher information and then inverted it and then looked at the uncertainty on omega hat or propagated that to uncertainty on P, you could then get at least the order of the uncertainty, and it's going to be very, very small. So that is not going to be a big problem when you're estimating this PL relationship. The uncertainty on the periods is not going to be causing a large amount of uncertainty on the estimate of that y-intercept. Yeah.
So does this become more of an issue when you don't have a light curve that's sampled as well as the one that you showed? Because then that uncertainty is way higher.
Yeah, so that's exactly that. So this is a very problem-specific statement, not something that is generally true. So a problem that I've been working on with some graduate students at A&M, plots here aren't so good. it's the same idea. You're estimating a PL relationship, but this is for Mira variable stars in this galaxy M33. They were observed very poorly here, so you can imagine how hard it is to estimate a period. And you can see a considerable amount of scatter here. And a lot of this is due to the fact that your point estimates are way off. So in this case, if you want to make a PL relationship here, it would be a very risky or probably not a good idea to just take point estimates for period here, put in those point estimates, and then say those are error-free point estimates. So one way to address this is a more challenging situation because you can't just ignore your uncertainty in your period estimates when making the PL relationship. One thing you can do is to try to make a hierarchical model, which is connecting uncertainty at different levels. So hierarchical models can be useful for propagating uncertainty through different steps in an analysis. So your final step is going to be estimating the y-intercept or just the linear relationship here, and you need to get uncertainty on periods, uncertainties on luminosities, and intrinsic scatter in the relationship. I think Tom Laredo will be talking about this, or at least in general hierarchical models, in October.
Just out of curiosity, do you know if anybody's tried any sort of measurement error style models, like adding a bunch of error on purpose and then extrapolating back to no error, like things that they try for errors in variable models?
Yeah, so you can. I don't think that's commonly done for people making PL relationships. I think they try to get well-observed light curves, or they just ignore them, or they throw out. So one thing you can do is if you have like some well-observed light curves and some poorly observed light curves, you can throw out the poorly observed ones, and then you have less data, but it's kind of higher quality. I think it's interesting because if you look at a lot of the literature on measurement error models, like I'm thinking Ray Carroll has a book, Modern Approaches to Measurement Error. They don't, or at least I haven't seen them, try to connect some sort of background data, or instead of just having this scatter plot with some given distribution or some estimated distribution on the x values, you have a potentially very complicated error distribution on your periods, but you can kind of get to it by very careful analysis of the light curve. So I think you could look at this as being a very rich or sort of complicated errors and variables problem, where estimating the error distribution is feasible, but it requires you to do some careful modeling of functions. Okay, so that's what I have for, that's most of what I have for period uncertainty quantification. We'll actually get back to it in a few slides. So far, all of the period estimation that I've been discussing has been using a single band of data, but frequently you have data in several bands. So here's an example of a light curve that's been observed in two bands, the I band and the V band. And you could consider this a well-sampled light curve. So that's not well-sampled is not a technical word, but you've observed it 100+ times in the I band. So you might suspect that you can get a very accurate period estimate, probably just using the I band data. So this is the folded light curve where the period was estimated just using the I band. So in this case, you have data where a period estimator based on a single band of data works well. That's probably not going to be the case when you move to more poorly sampled light curves. So this would be an example of a light curve where you have, I think, 10 observations in 2 bands. So you can imagine if you're trying to estimate the period for this object, it would be bad idea just to use the I band of data. You're really limiting yourself there, because that's probably not going to be enough to get you a decent period estimate. So you really want methods that make use of the 2 bands or the 5 bands or however many filters or bands you're observing these stars in. So one really simple idea is to just, and I think I mentioned this already, you can fit a sine function to each filter, to each band. And typically, in almost all cases, the period of variation is going to be the same for the different bands. So you'd have a common frequency parameter across all bands, but your means, your amplitudes, so that'd be beta B, AB, and phase, rho B, are different for each band. So now you have more parameters, but the algorithm and the software that you need for computing this is essentially the same as for a single band case. So we already went over this, that you can break up the sine function using the angle addition formula, and then you solve for your transform parameters. Now you have more parameters though, because you have a separate amplitude and separate phase for each band. And typically you'll do a grid search cross frequency. So this model will have a total of 3b plus 1 parameters. So that plus 1 is the frequency, which is common across all bands. And the 3b, so capital B is the number of bands or number of filters you're observing the star in, and you have 3 because you have a mean, an amplitude, and a phase for each band. So that can help you estimate periods accurately when you have several bands that are maybe reasonably well sampled. So you can imagine a case where you have 20 observations per band and 5 bands. If you just use a single band of algorithm to estimate the period, you'll tend to get very noisy estimates. But by using a simple multi-band extension like this, you can greatly increase the number of data. So you'd have 100 observations total, so 20 observations per band and 5 bands. And you'd have 16 total parameters. A problem, though, is that if you really want to push this down to very sparsely sampled data, where you have maybe 5 observations per band or fewer, then you're in this regime where you have a lot of parameters. So you have, with 5 bands, you're going to have 16 parameters, and you maybe only have 25 or fewer actual data points. So one idea is to try to build in, I'll back up a few slides here. Instead of just letting all these parameters be totally free, try to build in some of the physics that we know is going on with these variable stars. So one thing that you can probably tell right away is that, at least for this object, the phases in the different bands are pretty similar. So it's not as if you reach peak brightness in I band here and peak brightness in V band here. You have peak brightness in both bands at roughly the same point in phase space. So even though when you're fitting this multi-band, when you're fitting a separate sine function for each band, and you have, say, 5 different phases, one for each of your 5 bands, in reality, you expect all of these phases to be quite close to each other. Just to illustrate this, if you take 100 Cepheid periodic variable stars and you estimate their period, you can downsample them to 10 observations per band. And then you can compare the phases that you get when you, with the poorly sampled, the downsampled light curves, artificially downsampled, versus phase estimates from the full light curves. So what you get is the following. So this is on the full light curve. So the full light curves would have, you've made hundreds of measurements per band in these 2 bands, and then you fit the pair of sine functions, and so you get 2 phases, an I band phase and a V band phase. And you're not trying to force the phases to be similar, but you can observe that the phases tend to be very similar in the different bands. But if you, with the poorly sampled light curves, what you find is that the phase estimates don't necessarily exhibit much correlation. But you sort of know that this is, say, the maximum likelihood solution for one light curve has a phase of about 0.8 and -2. This isn't really a physically realistic pair of phases. That would be saying that for this light curve, the phase of maximum light was very different in the I and the V bands, but we know that that's not really true. So it would be good to have a method which sort of incorporated this information and forced phases to be similar, and this could effectively reduce the number of free parameters when you're fitting those sine functions. Something similar exists for amplitude. It's slightly more complicated. So the amplitudes in the different bands are highly correlated, but they're not the same. They tend to be the ratio of them, though, tends to be fairly constant. So this is the amplitude in the I band for these Cepheids and the amplitude in the V band. This is for well-sampled light curves where it's easy to estimate amplitude. And you can see that they tend to fall along this line, although this isn't exactly the identity line. The scaling here is a bit different. So the V band amplitude tends to be a bit larger than the I band amplitude. So this sort of observation can motivate a penalized likelihood approach to fitting these sine functions. So you have your original negative log likelihood here, and you have 3 capital B plus 1 parameters, so 16 total. If you have 5 bands, 16 total parameters here. This part of here there's everything's unconstrained, so you're not trying to force phases or amplitudes to be similar. But you can add penalty terms to try to enforce that scientific or physics understanding that we have of these light curves. And you would choose these J rho and J A functions to try to encourage phases and amplitudes to be similar. So computationally, roughly, you're doing the same thing for your frequency estimate. You're going to minimize this penalized negative log likelihood. But you're hoping that these penalty terms are going to encourage realistic estimates for amplitude and phase, and in turn give you better estimates of frequency. So what sort of penalty terms you can have? Well, for phase, the phases in different bands should be similar. So you can think that you want to shrink all the phases towards the mean phase in the different filters. So a natural sort of penalty to have for the phases is something like this, where the rho bar is the mean phase in the, say, 5 bands that you have. And then if the phase in a particular band B is far from that mean, you penalize it more heavily. And then you have a gamma 1 parameter to control how much you want to force phases to be similar. So you can think of this, if you let gamma 1 be infinity, then you would essentially reduce the number of parameters you have from 3b plus 1 to 2b plus 2, because the phase of every band would be the same. So you'd have 1 phase parameter, 1 frequency parameter, and then amplitude and a mean for each band. So that's if gamma 1 is infinity. If gamma 1 is 0, you're kind of back into the unpenalized framework. Is the overall picture making sense? Very simple.
So I understand the extremes, but don't you want to have a physical motivation for choosing the actual value of gamma somewhere in the middle?
Yeah, so what you do is you look at the kind of scatter that you see around these relationships. and then you can choose gamma 1 to push phases together, but not too much, essentially.
So that sounds fuzzy. I mean, is there a quantitative?
Yeah, so there's a few ways you can do it. So I've explored a few.
I'm pestering you because I want to do something analogous in my own research.
Okay. Okay, so if you want to approach this from the Bayesian perspective, you can look at these. I think that's quite helpful. You can look at these as just a prior on your phases, and then you can, since you have historical data, like we have lots of light curves that are on computers, and they're well sampled, like OGLE style light curves, and so we essentially know their phases, and then you can use that data to generate like a distribution for what phases are. Say for Septiids. So if you have a bunch more Septiids here, you essentially know a distribution for phases in the two bands, and then that penalty, that gamma 1 is going to be essentially a function of the dispersion that you see around the identity line.
Sorry, the problem I'm trying to map it onto is more complicated because if you want to impose a penalty on this physical property, not a measured property. So that might.
Okay.
I guess you kind of already alluded to this, but I thought it was going to be why not just correlated phasing, but you start adding on penalties to your priors.
Yeah, so I mean, essentially it is that. It's kind of like the lasso, or you can look at it in different ways. A ridge regression.
It's like you can interpret it either way. So frequentists will call it penalized regression, phasing, that's priors on things, right? But you can kind of depending on which approach you want to take, you can probably get a similar result out of both of them. So some people, like if your problem is extremely computationally intensive, running MCMC may just not be something that you can do. And if you can come up with some real slick computational algorithm that will do the same thing iteratively, then you might be okay. So it's sort of, you can probably, and I'm not speaking in any kind of way authoritatively, but you can probably get what you want out of either end of things. It's just a matter of how you want to get there.
Yeah, I'll just add as one kind of not final, but one note. There were some interest, as I've said before, these light curves are not exactly sine functions. And so you have a sort of misspecified model, and there was some interesting interaction there with trying to choose the gamma 1 in a Bayesian way, and the fact that the model was misspecified. So we kept on thinking that certain gammas would work really well, and then they didn't. And after a bit of work, we felt that the model misspecification was causing gammas which looked reasonable based on the spread we saw here to not actually be so good in practice. But that's a kind of a detail. Okay, so you can have this penalty on the phase, which you can think of as a prior on the phase. It's actually an improper prior on the phase. It shrinks phases to be similar across the different bands, but it doesn't try. Because it doesn't try to, it's a little bit harder to see in the phase. Let me try to. Yeah, improper has a technical meaning.
Yeah, it has a technical meaning. It's not bad.
Well, some people.
Like that's a bad prior.
Well, some people think no, but some people don't like improper priors, but other people don't have problems with them.
Other people think they're perfectly proper.
Yeah.
Okay.
Yeah, proper and improper have very specific meaning.
Okay, so is it something you can explain?
Yeah, so if you have a like a density, it should integrate to 1. But so if you have a prior can be a density, but a improper prior won't integrate to 1.
It really depends on how you're going to use it.
I think so. A lot of people motivate the Bayesian framework by saying that my prior represents my beliefs about the parameters before I collect any data, and I think it's a little bit harder to see improper priors as beliefs since they can't be normalized. Is that a fair statement?
Okay, so you can think of if you have a parameter and if you say that it can come from anywhere in the real time, so you can say that okay, the prior is flat and it can come from anywhere. But then you integrate it anywhere like a constant, then it's infinity, right? So it doesn't make sense. So improper prior is a belief that it can, I mean, you can think of it as a belief that is saying that it can come from anywhere. But this is just an example.
Yes.
Right, yes.
But sometimes, okay, sometimes believe in improper posterior, which is very much
Yeah, right.
People use improper priors all the time.
Well, I mean, it sounds like computationally, you don't have to, right? Because any computation you do, you can't just keep going on and on and on.
So you can do something similar for amplitude. You don't want to push all the amplitudes to be the same though, because as I said before, the amplitudes, the ratios between the amplitudes and the different bands is constant but not 1. So this is just this plot illustrates that. So this is for some well-sampled light curves where it's easy to estimate amplitude in the I band and in the V band, and you can see that they roughly fall along this blue line, but not along the identity line, the black line. So you don't want to use you don't want to shrink this way. Instead, we shrink towards the kind of expected ratio between the amplitudes and the different bands, and so that's done with a prior here. So the same idea, but a slightly different implementation. And you also have this gamma parameter, which we call gamma 2, and then gamma 2 controls how much you want to shrink. So again, you could set gamma 2 to be infinity, and then you would be forcing all of the amplitudes to lie on a particular line. Okay, so now you have it's a penalized negative log likelihood. We're trying to minimize this in a Bayesian setting. This is very similar to finding a map estimator with particular priors. The computation becomes more difficult here. So you can do something like I just very roughly sketched one algorithm for minimizing this. So the posterior or the penalized negative log likelihood, it's very spiky in omega. So you sort of have to do a grid search on the omega parameter. You can do a block coordinate descent for the beta, amplitude, and rho vectors. For the beta and the amplitude, there are actually closed form updates. This amplitude penalty is a lot like a ridge penalty. So if you keep everything else fixed and you want to minimize across amplitude, the solution is basically the same as ridge. The phase is more of a problem. So you do have this ridge-like penalty on phase, but it's not, the phase is no longer linear. It's not like amplitude's linear here, but phase isn't. So you can use majorization, minimization techniques to address that. But the message here is that if you want to, usually more sophisticated algorithms that are going to be able to do more with less data, there's a computational price to pay. There's a little trick in that you don't actually have to compute this penalized negative log likelihood at every frequency, because the penalized negative log likelihood is bounded by the residual sum of squares. So the idea is that you can compute the unpenalized method at every frequency here, and then that's going to give you some initial guesses at what the best frequency is. And then, so this is just based on the unpenalized version of the algorithm, this looked like the best frequency. So then you can compute the penalized negative log likelihood at that frequency. And then you know that the penalized negative log likelihood at all of these frequencies, say up here, these are going to have to be even greater than the points, right? So then I know that this is not going to be a solution, right? So I initially did the residual sum of squares, got this function, found my best candidate period, computed the penalized negative log likelihood. Anywhere where the residual sum of squares is larger than the penalized negative log likelihood, the penalized negative log likelihood at this point is going to be even higher, so then it's not going to be the solution. So you don't actually have to run this algorithm at every frequency. You can do the kind of fast, unpenalized version, and then at a small subset of frequencies kind of decide between them using the more refined method.
So this is really only helpful if your penalized log likelihood is much more expensive than your regular one. Like if you're just putting like a simple penalty on.
Yeah. We had the grids are sometimes like you might have to try 20,000 frequencies, and then it tends to be that you really only have to, when you're finding the penalized negative log likelihood, you only have to compare like 20 or 30 frequencies. So you can vastly reduce the number of candidate frequencies you have to try. And then the residual sum of squares is much faster than the penalized negative log likelihood. So.
Because that's a residual sum of squares from that linear.
Yeah.
Okay.
Has anyone used MM algorithms before? Oh, nice. Okay. Okay, so do people want to take a break or just go right through? We have about 20 minutes left.
Yeah.
Let's just go. All right. People who speak up win. So, yeah, always speak
20
up.
minutes till the next slide, or 20 minutes total?
I think about 20 minutes total. Okay, so we'll just go through. All right, so just some notes. I think that's the. Oh, okay. It's a little bit longer than I thought. All right, so just some notes. The computation time goes up. Also, it's harder to quantify uncertainty because you have these. I guess you can look at it from a Bayesian perspective, but quantifying uncertainty on for penalized methods, especially if you're choosing the gammas sort of like as a function of the data, that can be really hard. You're also tuning the model to more specific variable star classes. So one way you can think of the sine function is it's true that it's a bit misspecified, but it's also sort of general method, whereas once you start trying to understand the, once you have a method where you're using the ratio between the amplitudes in different bands, that is moving you towards particular variable star classes, because that might be different for Cepheids and RLIRA and for Miras. So there's a bit of a trade-off between more general models and tuning models to specific variable stars. And we'll see that in a few slides where we build a model for RLIRA that's very, very tuned for RLIRA. And there you can get a lot from a very small amount of data, but the model totally breaks down for non-RLIRAs. Okay, so to give a little bit of sense of how this works, you can do a lot of nice testing with variable star data because there's a lot kind of out there. So if you're developing a method for a new survey, well, you can take some data from an existing survey where you have well-sampled light curves and you kind of have ground truth, and then you can downsample it to kind of simulate what you're going to see from a new survey. So we took a few hundred well-sampled RLIRA observed in 5 bands from SDSS Stripe 82, downsampled them so they just had 10 observations per band, and then used this penalized negative log likelihood method to estimate periods. And this is what we got. So each point here is one light curve. On the x-axis is the true period. So we essentially have ground truth for this data because it is actually well sampled, and then we just downsampled it. And then we estimated this is PGLS, but it's really just the penalized negative log likelihood method. So we estimate the period with the penalized negative log likelihood method. And you can see that sometimes you could say the true period or very close to the true period, but then other times you're sort of way off. There are some patterns in the errors. Does anyone know what those patterns are? Caused by? So before you think about the patterns, think about the asymptotic results I was talking about before. So I said that if n is decently large, you're going to expect that you're estimating the period correctly. So your estimate, this is like truth here, and your estimate would be truth plus some scatter that's normal, right? That seems to be totally not true here. Like for stars that have periods of 0.6, it's like you're either exactly correct or very close to correct, or you're like way off, or you're down here. It's a very non-normal error. So this is the result. The patterns that you see are the result of something called pseudo-aliasing. So pseudo-aliasing is approximate aliasing. So the question is, what is aliasing? So if you observe the star's brightness at regular intervals, so if the time, if Ti equals I, so you're observing the star once per day at the exact same time, then the frequencies omega hat and omega, which share this relationship for any integer k, these are actually indistinguishable. So it's like an identifiability problem based on the design, which is caused by how you're sampling times. So the sampling of times is a lot like the construction of your design matrix if you're just thinking in terms of linear regression. And you know that if your design matrix is not full rank, then you can't estimate parameters in a linear model. So the times, they essentially become, some function of the times ends up becoming your design matrix. And for certain ways of, if you're observing regularly, then there are frequencies which are indistinguishable. So there's a little bit of math that just shows that a sine function with frequency omega is also a sine function with frequency omega prime. If you're observing things regularly, it's sort of easier to see this in terms of a plot where you're making observations every night. So these are the black points. And then these two, this data is perfectly described by two different sine functions with different frequencies. So that happens if you have regular spacing, and aliasing is a big problem with regular spacing. If you have approximately regular spacing, then you get approximate aliasing or pseudo-aliasing. That happens a lot in astronomy. So the data, the observation times TI are very rarely regularly spaced, but they do tend to be, well, they have to be at night because your telescope can only observe at night, and a lot of times you're observing at approximately the same time each night. So one way you can see this effect is you can take all of the times that you observed, so those are the TIs, and then look at the differences. So this is the time observing in band B for the ith plus 1 measurement, and then subtract off the measurement before that in time, and then look at that mod 1. So this is just telling you essentially the time of day at which you're observing. And I did this for all light curves, and you make a histogram, and you can see that you're not, you tend to sample at about 1 hour intervals, or about 24-hour intervals. You're missing a lot. You miss a lot of nights too, but almost always at the same time each night. So that causes this pseudo-aliasing, and you can actually predict the error distribution. So these curves here are just generated from this relationship for different k's, and then you can see where you're going to be making mistakes. So this is a kind of interesting result. So you have this asymptotic result that says eventually things become normal, but at finite n, not only they're like not particularly normal, but they're like totally strange. Nothing that the asymptotics is totally misleading here. The asymptotics would be a much better approximation if the sampling of the times t had been more random. Okay, so that's a little bit about multiband period estimation. Are there questions there? Okay, so now I'm going to talk about the last topic for time domain astronomy. About this sort of involves two topics. One is about making models for specific variable star classes. So this gets a little bit back to the whole classification that we talked about on the first day of lecture. We talked about classification and doing feature extraction. So you get a bunch of these light curves, you compute a bunch of features, and then you throw those features into a machine learning classifier and measure your error rate with cross-validation or training test sets. A very different approach to doing classification is to build models for the different classes. We know a bit about physics of how these work. We can build models, and then we can compare models using things like Bayes factors or likelihood ratio tests. So I'll talk a little bit about a database model for one particular variable star class, and then how you could use those to find structure in the Milky Way halo. So that's an application. Okay, so we've seen these light curves a lot. This is an example of a RR Lyrae variable star detected by Sloan in stripe 82. And this is the folded light curve, and it has this nice pattern. And we can see features that we talked about earlier, like the phase seems to be similar. The phase of maximum brightness and phase of minimum brightness is similar in the different bands. So in stripe 82, that's a small section of the sky. This survey, SDSS-3, collected about 60,000 variable stars. It collected about 1 million total stars. Then they found a subset of 60,000, which they thought were variables. As we know, these variables belong to different classes. So I've plotted 3 variable stars here. So this is the unfolded light curve for an eclipsing binary. So this is when you have 2 stars orbiting around each other. And then that's a type of periodic variable. You can see the periodic variation here. So this is this is one star, and then here's a quasar, which is a type of non-periodic variable, and then the RLI array from the last slide. So what kind of science can you do with this? Astronomers are interested in how galaxies form, and they've created simulations and then made videos based on these simulations to understand galaxy formation. So this is an example of the output of one of their simulations. So what you're watching here is the formation of a spiral type galaxy. So you have a bunch of matter here, stars that are gravitationally bound and interacting with each other. And slowly that matter is coalescing into a single galaxy. But these kind of smaller galaxies are pulling each other apart. And it's sort of not clear as to who's going to be the winner. It's kind of an unpredictable process.
So
Or at least there's a lot of chaos.
Gauzy stuff is actually gas.
Oh, all the green stuff is gas?
The green gauzy stuff is gas.
Okay, and then in the center are the stars?
Yeah.
Okay. All right, so most of what you're seeing is gas, some stars. So one thing in particular is that these simulations, they predict that there'll be a lot of structure, or in particular stars, on the edges of the galaxies. So you can kind of see this. Well, maybe this is gas, but there should be like small collections of stars outside of the Milky Way spiral, and those stars are going to be dwarf galaxies or satellite galaxies. They're smaller galaxies, so collections of hundreds, thousands of stars that are gravitationally bound to the Milky Way. It's very difficult to detect those because they're not particularly bright. But by detecting them, we can compare what these simulations predict to what's actually out there. If we don't find anything, maybe that's saying the simulations are wrong. If we find more stuff than the simulations predict, maybe the input parameters to these simulations need to be tweaked. So one way that you can find structure in so that area, the area kind of outside the Milky Way, near the Milky Way, but outside the spiral arms, that's called the Milky Way halo. So one way that we can figure out what's in the halo is through RLI array variable stars. So RLI array variable stars, they're a type of periodic variable. I showed some of the plots I was showing before were of RLI array. And their distance is a function of their mean brightness. So we talked about how it's hard to determine distance to objects in astronomy, but if you have an RLI array variable star and you know its mean brightness, then you can back out its distance. So that allows you to make maps of the structure that you see in the Milky Way halo. So in particular, for SDSS Stripe 82, they were looking at this very narrow strip of sky here. So Stripe 82 is just this green strip. And they found 60,000 variable stars. Of those, they found about 400, which were RLI array. And then they made essentially then for all of those RLI arrays, they computed distances to them, right? So initially, you don't know the distance to these stars, but since you found that these stars were RLI array, you can compute the distance to all of them using this relationship. And then you know where your telescope was pointed, so you can create a map of the structure that you see in the Milky Way halo. So this is the map that was created by a team that analyzed the SDSS Stripe 82 data. And then you can compare this to what these simulations are predicting. Do you see a lot of smaller structures all over, or do you see single large structures? A lot of qualitative comparisons you can make. So Stripe 82 looked at a very narrow region of sky. You can see it's almost